Good morning, friends. It gives me immense pleasure to be here again for this class, which is the problem solving exercises for entropy changes. Before that, we have done for work transfer to heat to work, internal energy to heat to internal energy, all the things we have seen. And now in this topic, we will see that how the entropy changes are taking place for the different scenario, and that we will see. And in this we have numerical one, entropy changes in a lake. So we will have a lake. From there, how much entropy is changed, a numerical is there on this basis. Numerical 2, changes in entropy of systems and the universe. Numerical 3, direction of heat transfer. This will be our topic. In the previous class, we have discussed about numerical 1 for the Carnot cycle efficiency calculation. Numerical 2, Carnot cycle source temperature calculation. Numerical 3, reversible cycle heat transfer calculation. Numerical 4, refrigerator coefficient of performance calculation. We have done it in my just previous class. Today, my numerical number 1 is a 40 kg block of aluminium is at 450 kilo Kelvin. It is thrown into a lake. The temperature of water in the lake is 283 Kelvin. The block attains equilibrium with lake water after some time. So the temperature of the block is 450 Kelvin and the lake is 283. So the 450 Kelvin has reduced to 283 Kelvin. So it is called the equilibrium. So we have to calculate the entropy change for aluminium block, entropy change for the lake water, and total entropy change in the process. So how much entropy of lake is changed and how much entropy of aluminium block, which is having temperature of 450 and the mass is 40 kg. So this all the 3 cases for entropy change of aluminium block, for entropy change. So if you see here, this is the one block of aluminium and there is a lake. This lake has got the 283. This is the lake, 283. This is the 40 kg and the temperature is 450 Kelvin. This is so how much entropy, if we are throwing from here to here, what will happen and how much entropy is going to be changed for aluminium block, for entropy of the lake, and for the total entropy of the full process. This is we are going to discuss in this problem. So here we can see that for the aluminium block, the mass is 40 kg, T1 is 450 Kelvin, water is at 283 Kelvin. So we have to find out that change in entropy of aluminium and change in entropy of the lake, and then delta S total to be find out. These are the things which we have to take care of, and this has to be done. So find that final temperature will be equal to the lake temperature. So for this T2, for this T2 of the block will be 283 Kelvin. So we can find out by this that TDS is equal to DU plus PDV. Oh, okay, because this block is solid block. So there is no change in volume. So this PDV work will be 0. So here we can write that TDS is equal to DU. So DU is equal to mCdT. C is specific heat of aluminium, which is 0.9 kilojoule. So here M, so ds TdS is equal to mc dt. So ds is equal to mc dt by t. So s is equal to integrate it 1 to 2. 1 to 2. So you will get mc ln t2 by t1. M is equal to 40, c is equal to 0.9, log t2 is equal to 283 and t1 is equal to 450. So you will get minus 16.69 into 10 to the power joule per Kelvin. Minus due to aluminum loses heat in lake. This minus indicate that this is losing its heat in the lake. So that is the indication that this is the minus has come. So for the block, it is a minus 16.69 10 to the power 3 joule per Kelvin or minus 16.69 kilojoule per Kelvin. That is the your entropy. Now change in entropy of a water. So how much the water it is changing? So it is T is given 183 Kelvin. So TdS is equal to du plus TdV. So here we can see that this a block giving out dq heat will be dq of the water. So how much heat is given by the block is giving to the water. So here we can write that TdS is equal to del Q. TdS is equal to del Q. So this delta S is equal to Q by T. Q is equal to here 40 into 900 283 minus MCV T2 minus T1. So 283 minus 450. So it will come minus 6 megajoule for aluminum. So for water how much? It is plus 6 megajoule of heat for the water. So now here ds entropy change in the lake, ds is equal to del q by t. So del q is equal to 6 into 10 to the power 6. So here we have to find out this del q. This is the del q is equal to mcp t2 minus t1. So here 6 into 10 to the power 6 divided by 483. So 21.2 kilojoule per Kelvin. This is the change in entropy of the water. This much water will be this much entropy will be changed. So total entropy change is equal to delta S of aluminum plus delta S of water. So aluminum is minus 16.69 into 10 to the power 3 joule per Kelvin plus 21.2 into 10 to the power 4 joule per Kelvin. So this delta S will be 4.5 into 10 to the power 3 joule per Kelvin or 4.5 in kilojoule per Kelvin. So this is the answer, that this much a universe or full total change of entropy will be plus 4.5 kilojoule per Kelvin. Increase in entropy is observed in this problem. Here entropy is not zero. So here it is positive value. So there is a losses of this thing. Entropy of universe always increasing. So if it is a universe, it will be always increasing. Individual, it can increase or the decrease. But for the system and the surrounding, the total entropy will be always positive. That we have to take care of. This value should never go negative. Never it should go negative because it is not possible. Okay, so that we have to take care of. Now I will go for the second problem. In this second problem, is a system consists of 2 meter cube of hydrogen. This molecular weight of 2 kg per kilomole, gamma is equal to 1.4. Initially at 35 degrees centigrade, 215 kilopascal, contained in a closed rigid tank. Full stop. Energy is transferred to the system from a reservoir at 300 degrees centigrade until the temperature of hydrogen is 160 degrees centigrade. The temperature of the system boundary where the heat transfer occurs is 300 degrees centigrade. Determine the changes in entropy of the system and the reservoir. What is the change in entropy of the universe? So here systems, surrounding and the total universe we have to see for the given condition. In this 2 meter cube of hydrogen of molecular weight and all things are given. Its initial temperature is 35 degrees centigrade and 215 kilopascal in a closed rigid tank. Energy is transferred to the system from its reservoir at 300 degrees centigrade until the temperature of H2 is 160 degrees centigrade. The temperature of the system boundary where the heat transfer occurs is 300 degrees centigrade. Determine the changes in entropy of the system and the reservoir. What is the change in entropy of the universe? That we have to find out. So here, initially it is 300 degrees centigrade, 2 meter cube, the hydrogen. So temperature is 35 degrees centigrade. P1 is 215 kilopascal. It is a rigid tank. T2 is equal to 160 degrees centigrade. The gamma is equal to 1.4 and the molecular weight is 2.8 kilomole. It is given. Change of entropy of hydrogen, we know that TdS is equal to du plus PdV. The tank is rigid, so dV is equal to 0. So this is work done is equal to 0. So TdS is equal to du and this is the CV dt. So ds is equal to CV log T2 by T1. So delta S is equal to mCV log T2 by T1. M is given this much. M CV is 10393 and 433 by 308. So you will get here change in entropy ds is equal to 118. This is the, you will get this thing here. So now H2 as an ideal gas, mass not given, so we have to find out the mass. This mass we have to find out. So how to find out? PV is equal to MRT. So here M is equal to PV into divided by R into T. So you will get here mass is equal to 33.58 kg and this CV is equal to R by gamma minus 1. R is equal to 83145 divided by 1 minus 1.4 minus 1. So you will get, it is hydrogen, so it is H2. So we are dividing everywhere by 2. So here also if you see here divided by 2 and here also we have divided by 2. So here you will get CV is equal to 10393. So 10393, this we have taken from here and we have put here. Mass also we have taken from here and we are putting here. Okay, so in this way we have to find out the mass and we have to find out the CV. This mass and the CV we have to put in the mCV log T2 by T1 and then we will get the answer of this entropy change. Now to find the delta S for the reservoir. So for the reservoir, T into delta S is equal to Q. So delta S is equal to Q by T, Q by 673 Kelvin. So delta S is equal to minus 428 by 67. So from where this Q, this we have to calculate from here to here. Using first law of thermodynamics, du is equal to del Q minus del W. So du is equal to 0. So del W is equal to 0. Del U is equal to del Q mCV delta T. Now to how to find out CV? CV is equal to R by gamma minus 1. So R is equal to 8314.5 divided by 2 1.4.1 CV, you will get 10393 joule per kg Kelvin. Now delta Q is equal to mCV delta T. M is equal to 0.33 into CV is equal to 10393 and delta T is equal to 160 minus 35. So Q you will get 428 kilojoule for hydrogen. This value will put in the equation 1 here. Okay, so this is the minus 428 kilojoule for reservoir. So minus 428 divided by 673. This you will get minus 0.637 kilojoule per Kelvin. So this is for the reservoir. Now entropy change in the universe. So it is a delta system plus delta S reservoir. So delta S is equal to 1.18 minus 0.637. So initially we got the 1.18 for the system, and for this here we have got minus 0.637. So net entropy 0.543 kilojoule per kg. This much entropy increase for the total mass system, and this is the positive. This is the consequence of the second law of thermodynamics. So this is happens due to the second law of thermodynamics. There will be always losses. This indicates that there are losses, and that is why the second law of thermodynamics, from there only we have got the value of entropy by the help of the second law of thermodynamics. So I am going for the problem number 3. The problem number 3 is very simple and very small. So a heat source at 800 Kelvin loses 2000 kilojoule of heat to a sink at A 500 Kelvin and B 750 Kelvin. Determine which heat transfer process is more irreversible. So here we can see that a heat source of 800 Kelvin and 2000 kilojoule of heat to a sink of 50 Kelvin and 750 Kelvin. Determine which heat transfer process is more irreversible. Okay, so here we have the two system, the system 1 and the system 2. So here the heat source is 800. Here also it is 800. It is supplying 200 kilojoule for both the system, but here the sink is taking 500 Kelvin and here it is a 750. So by this only you can identify which one is having more irreversibility. So in this, if you see the efficiency 1 minus QL by QH. So here as much you have less QL. If QL is less, then efficiency will be high. So in this, if you see, this one has got less, it is less QL comparing to this. So this has got more reversible. This is the more irreversible. This is a more irreversible, and this is the reversible. This is better than this because the losses here are less than this, because more 800 to 500, here 300 is consumed and here only 50 is consumed. So that much, so we can say that the system 1 is better than the system 2 because system 2 has the more irreversibility. So the further we will discuss here in our heat is transferred from a heat source to two heat sinks at different temperatures. The heat transfer process that is more irreversible is to be determined. So this is our objective, and how to go about. This is our figure. So here for the heat transfer process to a sink at 500 Kelvin. So delta S source is equal to Q source by T source. So here it is minus 2000 kilojoule by 800. So you will get minus 2.5 kilojoule per Kelvin. Now delta S for the sink is equal to Q sink by T sink. So here 2000 by 500, it is a plus 4.0 kilojoule per Kelvin. So S generation is equal to delta S total, delta S source plus delta S sink. So minus 2.5 plus 4.0 kilojoule per Kelvin. So that is the 1.5 kilojoule per Kelvin. So that is the first, we have observed that this much it is, answer is obtained. So total generation of the entropy is 4.5 kilojoule per Kelvin. Repeating the calculation in part A for a sink temperature of 750 K, we obtain here that delta S of the source is equal to minus 2.5, but for the sink, if you divide by here 750, you will get plus 2.7 kilojoule. So if you net entropy generation, if you see here, delta S generation is equal to minus 2.5 plus 2.5 kilojoule per Kelvin. It is 0.2 kilojoule per Kelvin. So we can see that net entropy generation for the second process is 0.2 kilojoule per Kelvin. So if you see the losses in the case 1 for the heat transfer process at 500 degrees centigrade, in this losses are more or entropy is more, but in this case the entropy is less. Okay, so these are the references which I am using, that is Eunice Sengel, Michael Ebol's Thermodynamics and Engineering Approach, Tata McGraw-Hill's, and also I am using this reference for NPTEL lecture from IIT Kanpur, Professor Mishra, a very nice lecture. If any questions, you are welcome to ask. My email is ydvedi@gmail.com. This is my email. You are always welcome to ask any questions. Also, I request to like and subscribe this channel, and hope these things will be very useful for your study on the thermodynamics. And any questions, I will be very happy to answer. Thank you very much for joining. Be tuned for my next lecture. Very interesting topics will be coming. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.